So this series of movies is going to be a crash course in star formation. Star formation is really a fascinating subject, and how many fields of science can say that they've appeared in artwork such as Van Gogh or Kandinsky. Both of these images to me evoke star formation because they have lots of features of things that you find in star formation. You have all sorts of turbulence, and you have clouds with condensations within it. I really love star formation. I hope you guys will love it too. So why should we study star formation in the first place? I mean, it lends itself to many different questions. For example, how do stars like our sun form? Our sun is an average run-of-the-mill star, but how do more or less massive stars form? How do the really big stars form? And is it different than how do the really little stars form? And how do most stars in the galaxy form? And do they normally form in groups? Do they form by themselves? How does a forming star interact with the circumstellar disk around it? Does every planet, every star have a planet? And ultimately, how do planets like Earth form? Studying star formation has bearing on all of those things. And moving out in distances, by studying star formation, you have questions about how do galaxies form? How does star formation affect galaxy evolution? And how do most stars in the entire universe form? Do they mostly form in spiral arms of galaxies? Or, how often do you get stars forming much further out? Are there planets around the oldest stars? And how did the first stars form in the first place? Looking closer to home, trying to understand our own solar system and others like it, did Jupiter form exactly where it is now, or did it form someplace else and then migrate into where it is now? The best theories right now have Jupiter migrating quite a bit in and then back out again. Is that really what happened? Did we ever have other Jupiters that form exactly where they are or migrate in other solar systems? Did they form where we see them now, or did they migrate? If Jupiter migrated, did it actually significantly throw asteroids around the solar system? If it migrated, it almost certainly did. And is that the cause of something called the late heavy bombardment, which explains a lot of the craters on the moon? Did we need the late heavy bombardment to actually get the water on our blue marble that's so full of water and so critical? And having water is so critical for life. Do we need something like the late heavy bombardment in order to get water on rocky planets? Did we need the moon in order to survive the late heavy bombardment? Did we need having the moon in the way to help shield us from the worst of the impacts? And did comets bring most of the water to Earth? Trying to understand star formation has bearing on all of these things too. But it's also good to keep things in perspective. Here's the page that link points to. It's something called the Illustrated Guide to a PhD. And what it says here is, every fall I explain to a fresh batch of PhD students what a PhD is. It's hard to describe it in words, so I use pictures. Imagine a circle that contains all of human knowledge. By the time you finish elementary school, you know a little. By the time you finish high school, you know a little bit more. With a bachelor's degree, you gain a specialty. A master's degree deepens that specialty. Reading research papers takes you to the edge of human knowledge. Once you're at the boundary, you focus. You push at the boundary for a few years, until one day the boundary gives way. And that dent that you've made is called a PhD. Of course, the world looks very different to you now, but don't forget the bigger picture. Keep pushing. So it's good to keep things in perspective. Our project is less of a dent in the overall worldwide knowledge of star formation because it's not a thesis project. We have to do this within a year, but still we're working on something very, very tiny. It is part of the bigger picture. It is contributing to the worldwide human knowledge, but so we're going to get into it really, really tightly. We're going to focus really close in, but it's good to remember the big picture in a lot of different ways. So a lot of the stuff that's covered here is based really heavily on the talk that I give to amateur astronomy groups and similar audiences, but there's several pages on the wiki that include a lot of this information and more, and the movies that I'm going to show are linked in there too. If you would like to use the movies to explain star formation in other contexts, by all means, please grab them. They're all public domain. They're all part of the Spitzer press release archive done by our really fabulous animators here at Spitzer. So this is a relatively nondescript globule called IC1396. This is an optical image. And this thing is in Cepheus. It's about 3,000 light years away. This image is about the size of the full moon. it's part of a complex. This globule is part of a complex that's 10 full moons across. So it's part of an enormous complex. And somewhere over here on the far left is a small cluster of O and B stars. And they're putting out so much radiation, so much ultraviolet light, that it's pushing the gas and dust around. And it's pushing this globule around. It's pushing the dust in this direction. And so because of the light, because of the filters that they've chosen to make this image, that red is H-alpha. And you can almost see the stuff boiling off the ionization front here, because as that ultraviolet light comes in, it's going to burn off, much like the sun burns off fog. It's going to burn off this tenuous matter, but it's going to reveal stuff that's hidden inside. This hole here is almost certainly a result of a star whose formation was prompted by the pushing of gas and dust around, and it's starting to blow its own hole in the interstellar medium there. So when I hit the button, it's going to fade into an infrared image from IRAC, from Spitzer. So it's going to allow you to see inside all of that gas and dust that's dark in the optical. See how much that changes as you move from the optical into the infrared. You can see lots and lots of point sources in here. Now, many of these point sources are not in this nebula, but behind it. So one of the things that the people who studied this did, and that we're going to do, is try to identify the sources that we think are part of, in our case, IC 417, in their case, IC 1396. So just for an example, let's look at these point sources here. If I go back to the optical, there's one here that's very bright, and we can't really see the others. It's that guy right there. And when you go in the infrared, he's got several friends that are all of comparable brightness, but he's the brightest. There's another one in there. Here's another view of it. IC 1396. Now we've included slightly different bands, including MIPS 24 microns. And the color scheme that's been combined here results in anything that's molecular hydrogen, H2, is in green, and everything that's in brown is polycyclic aromatic hydrocarbons, rings of carbon, otherwise known as the grunge on your grill. They're found everywhere in the universe, from the most distant, earliest forming galaxies to the comets that are right next door. They're everywhere, and they're in the category of organic molecules because they're aromatic hydrocarbons. We don't know exactly how they form. They have really complex spectra, a lot of lines in the infrared, and so some of the filters that are chosen for infrared observations are chosen to match some of the emission and absorption lines that come from PAHs. Here's an overview cartoon that talks about how a low-mass star forms. You're going to start with a big cloud of gas and dust, and there's going to be condensations within it. Look at the length scale here. That's 200,000 AU. Remember, an AU is an astronomical unit, which is the distance between the Earth and the Sun. We're going to zoom in on one of these dense cores, and we're going to watch the gravitational collapse happen. Note that we've gone from 200,000 AU to 10,000 AU length scales, and we're going to start the clock. Things initially are going to fall straight in. But because this big cloud is almost certainly rotating very, very slightly, as the stuff collapses, angular momentum must be conserved. It's one of those things like energy that has to be conserved in all of physics. So in order for angular momentum to be conserved, things don't exactly fall straight in. They fall into a disk from which it spirals in to the central object. And so here, this is what you have. So notice the length scale has gotten smaller. We're now at a length scale of 500 AU because gravity has been winning. Gravity has been pushing in. And it's about 10,000 to about 100,000 years. So you have in the outer edges of the envelope still stuff falling radially in. But when it gets closer, it starts to fall into a disk and then spiral in to the central object. And for reasons nobody understands very well, but are almost certainly related to magnetic fields, some of that incoming matter turns right around and gets ejected above and below the disk on the magnetic poles. Now, in doing this, I'm assuming that the magnetic axis and the rotation axis are nearly aligned. They may not be. We don't really understand. The jets go out on the magnetic axis, not the rotation axis. So you have these big flows of matter going out above and below the disk. Eventually that envelope thins out and you're left with a big disk and still jets going on because the accretion rate is still very high. Note that we've gone from 500 AU to 100 AU because gravity is still winning. Gravity is still pushing things in. And the time scale now is 100,000 to 3 million years. This is still a very young star. Eventually, that disk thins out, and because the rate of mass accretion slows, the jets turn off, and you end up with a disk that is almost certainly forming planets. The length scale now is about the same. About 3 million to about 50 million years is about the time scale for planet formation. Eventually, you end up with a genuine, bona fide, hydrogen-burning, mortgage-paying adult star with a planetary system around it. The length scale is about 50 AU, and this is about 50 million years old. So these are the adults, these are the teenagers, these are the real babies. Throughout all of this, gravity's been pushing in. When hydrogen finally ignites and it becomes an honest-to-God star, not just a forming star, but a star, it's starting to burn hydrogen, turn hydrogen into helium. And at that point, now finally there's something pushing back against gravity. So gravity's been winning, but the relentless pressure of gravity is halted for a little while hydrogen is burning in the core. Depending on the mass of the star, you may work your way up the periodic table till it runs out of fuel, and then gravity ultimately wins by pushing in. So here's a movie, an artist's conception, that will help put those cartoons in context. Here we have a big disk, some outflows coming off. We're going to zoom in on grains in the disk. These grains are going to be distinctly green because they are olivine, like green sand beaches in Hawaii, and they are being covered in ices of all sorts, water, carbon dioxide. These are things that are known to be in protostellar disks, olivine and ices. This next movie starts out the same way, but instead of looking at the stuff in the disk, we're going to look at the stuff in the center. In the center, there's going to be the young stellar object at the center, but we're going to start forming planets. And that planet is going to scoop up matter. He's going to show up visibly about here. So you see that protoplanet has swept up the matter in that inner part of the disk, creating a hole in the inner disk. And that matter has gone onto that little protoplanetary object. You can have this happening in many different places in the disk at once, and so you end up with protoplanets at a variety of radii, collecting up matter, creating gaps in the disk. So where else have you seen this same physics operating? In Saturn. Saturn's rings are exactly the same physics, but at a different scale, a different central mass, a different radius of the disk. But it's the same idea. You have moonlets in Saturn's rings. They create gaps and arcs and texture in the rings. And you have moons that shepherd the rings in order to, it changes the structure of the dust in the disk. So it's exactly the same physics. It used to be that this is all I could show you as an analogy for what's happening in protostellar disks. But recently there have been this spectacular data from a nearby star called HL Tau taken with ALMA. This is a radio telescope, and this thing is only 140 parsecs away. So this is among the closest young stars to Earth that we know of. And you can see, so there's the central object, and you can see there's all sorts of gaps in the disk, which is fascinating. When this image was released as a press release, there was so much traffic on social media. It was just fascinating to watch the astronomical community try to do science with this JPEG, because that's all it is. No actual data were released, just the JPEG. And so people were very, very excited, trying to figure out what the resolution was, trying to figure out whether the gaps meant there were planets or not. And there were theorists saying, this is exactly what I predicted because of this. And theorists saying, but it should be spiral arms. Why isn't it spiral arms? All sorts of really incredible discussion. And this is just among the first observations of young stars that have come out of ALMA, and there's going to be a lot more spectacular data to come. But I wanted to show this specifically because it really does show it's the same physics as you get on Saturn. Now, it's more complex because the disk is a lot denser and a lot thicker, in all likelihood anyway, and it's not entirely clear whether every gap there has a planet in it or whether you end up with resonances where you end up creating a gap because you have a planet further in or not. But the data revolution is starting from ALMA. There's going to be a lot more really cool data coming out of ALMA in the near future. So here's another movie, Artist's Conception again, because when you have these protoplanetary chunks moving around in the disk, Sometimes they hit each other, and when they hit each other, they create a second generation of dust. The reason I'm mentioning the dust is, of course, what we're most sensitive to in the infrared. We're seeing the dust, whether it's a first generation of dust left over from the formation of the protosolar system, or the second generation of dust that comes from collisions of protoplanetary objects. So when you have lots of protoplanetary objects in your protosolar system, you can have temporary rings and arcs of dust be created as these things hit each other. And eventually, of course, the dust gets swept back up just like it did initially. But you end up with these temporary rings and arcs of dust in these young systems. So here's another movie that is zooming out to the edge of a solar system. This is meant to be like a Kuiper Belt. And I used to say that the Kuiper Belt is what's left over of our disk from this formation of our solar system. It is not at all clear anymore whether it really is entirely leftover detritus from the formation of our solar system. It may be that a lot of the population of the Kuiper Belt was arrived there as a result of scattering by Neptune as Jupiter and Saturn and Neptune migrated in and migrated out again. If you do models, there's a significant fraction of the Kuiper Belt that may have been scattered into it. But still, nonetheless, the Kuiper Belt is still interesting. And when we try to understand what the conditions were like in the early formation of our solar system, the Kuiper Belt provides incredible clues to the chemistry, to the chemical evolution, to our understanding of when rocks formed and how and why and where. So that's part of why people get excited when working with stuff in the Kuiper Belt. The Oort cloud is out further still. The Oort cloud is almost certainly what's left over of our original cocoon of matter. And that is part of why people get so excited when new comets come in from the Oort cloud, because they too are telling us something about the primordial chemistry, the primordial makeup of our cloud, of the cloud that became the sun and the solar system. It's telling us, it's giving us hints of what that very early solar system must have looked like. So now let's go back to this IC 1396 globule, armed with this understanding of how stars form. We've got the visible light picture here, we've got the IRAC image here, and we've got MIPS at 24 microns here. So there's the edge of the cloud. Remember, the bright star is over to the left. There's a star, and here it is, and he's got 4 friends that are comparably bright in IRAC bands. And that one, which is this one, is bright in MIPS. So probably what's going on is that this one is the least dusty because it's bright enough for it to be quite bright in the visible. But when you get to MIPS, this one is the brightest. So it is probably the youngest, or at least the most embedded. It has the most dust around it. And so you have already in this little grouping of sources, you have ideas about which one must be the oldest and which one must be the youngest, assuming that cartoon that I've told you, that story that I've told you, is correct. And if you look, you'll see other examples of that same sort of thing happening elsewhere in this little clump. So this is everything I was just saying, but with more information. The massive star is HD 206267. It's off to the left, and it is producing the head of the globule and the swept back tail of gas by its winds and its ultraviolet light. And the 2 young stars that are in that hole in there are, you read that Lick H alpha 349 and 349c, and they're blowing a hole in that. And there's 6 objects that are newly discovered protostars in this region because of the infrared data. A few of those stars that are easily seen in the visible light, they have a little bit of infrared excess emission, and that is probably what is remnants of their dust, or a second generation of dust from asteroids and comets hitting each other in their planetary systems. So this is just another cartoon showing that process, right, where you have the bright star, in this case to the upper right, and it's pushing the gas and dust, boiling some of it off, but also pushing it around, resulting in these sort of comet tails shape. It's the same kind of physics as you get if you have a large stone in a stream. If you play around with that, you can have the stone the large stone in the stream shield the mud behind it from the onrushing water. Exactly the same physics, just in space. So here's another situation where this is happening. This time the big bright star is up near the top somewhere, and it's pushing back the gas and dust, in this case not prompting formation of individual stars, but whole clusters of stars at the ends of these fingers. So this, I've shown you this image before. This is the M16, the talons of the Eagle Nebula, otherwise known as the pillars of creation. Remember, this is a tiny field of view, but all of the fingers at the end of that are the same physics, right? It's the same idea of having the ultraviolet light pushing around the gas and dust. And so now let's go and look at data that go with each one of these stages. So this is one of the very earliest clumps. So in other words, this very earliest phase, looking at these clumps. And people look for these very earliest clumps to try to understand, have they started forming stars yet or not? And what are the physical conditions of these clumps, so we can try to understand when star formation is initiated. So this is a clump that used to be known as the starless core L1014. The problem is that when we looked with Spitzer, it is not starless. There is very definitely something inside of it. And the people that wrote this, that did this research, that wrote this paper, worked really hard to show that this thing is really in this cloud and not a background object. It really is. It's in there. It turns out to be a baby brown dwarf. It's only 600 light years away, too. Here we have some examples of young star spectra. Remember that spectra are breaking up the light like a prism. So here's brightness as a function of wavelength. And remember in the movie we had these grains of olivine and dust. These are HST images in the near infrared here on the right, and these are infrared spectra from Spitzer. This is from water ice. This is from really complex ices, including methanol. This is something that astronomers call amorphous silicates, but you can really think of them essentially as beach sand. This is from carbon dioxide ice. You can see that there's similar structures in these two disks and in many others. A lot of people from NITARP that I've worked with have been very excited about HH objects. They are really, really cool. So let me have, even though we're unlikely to find any in what we're doing, let's spend a little bit of time talking about them. In order to get an HH object, you need a jet or an outflow. And because the very nature of that is that it's a transient feature of young stars and that stellar evolution, you have to be really lucky to catch it in the act. In order to have a jet at all, you need a big disk and you need to have a really high mass accretion rate. The stuff needs to be just pouring onto the star. And moreover, not only do you need that high accretion rate, you also need something for the jet to hit. If there's nothing in the way, then we will never see it because the jet will just keep on cruising out. But by hitting interstellar medium, then it causes all sorts of interesting shock physics, and you are able to see the energy from that shock as it hits in the form of line emission from the matter that's in that clump of interstellar medium. Remember that on these timescales, things are moving. So the star is moving through the cloud in which it formed. And remember that the jet axis, the jets are coming out on the magnetic axis, might not be exactly the same as the rotation axis. So you could get precession, you could get braided jets and spiral jets as the star is rotating. So here are some real images of jets. This is the dark cloud. You can't see it through it at all in the optical, but when you look in the infrared, you can see that there's a young star in there. You look really closely, there's an edge on disk, and you can see the jets coming off and creating huge amounts of light in the infrared that you really can't see in the visible. Here is a spectacular image of a huge jet called HH47 with HST. That, with Hubble, that little guy in the middle is responsible for these huge, huge jets. And you can see that it is slowly spinning because this jet goes down and comes back up. This jet goes up and comes back down. So you can see there's definitely some movement of the jet with time. Because remember, the stuff that's out here must have been emitted a long time ago from the stuff that's here, which was emitted a long time ago from the stuff that's here. And even over human lifespans, you can see stuff move in these jets as it's moving out in the jet. This is a slightly older system. This star is called Fomalhaut. It is the 18th brightest star in the sky, and it's only 25 light years away, but you've probably never heard of it because it's in the southern hemisphere. So we're talking about this stage in those cartoons. Here I have an image at 24 microns, and here I have an image at 70 microns. and I've subtracted off the contribution from the central star. So this is just the dust that's near the star. This is the dust that's further out. The best way that I can think of to explain this is sort of like a jelly donut. The 24 micron is showing us where the jelly is, and the 70 micron is showing us where the cakey part of the donut is. If you look really closely, though, you can see that it's asymmetric. You can see there's more stuff here than there. Remember in the video, I was showing you temporary arcs and rings of dust. This is almost certainly, the reason this is brighter is almost certainly because it's got a temporary arc of dust that's on this side, but not on that side. So it almost certainly is forming planets here. There is a couple of planets that people are pretty sure they've seen here. This is a disk that we've known for a long time. It's one of the dozen stars that IRAS discovered to have a disk. And this is an image in 450 microns, so much longer wavelength than 24 and 70. And you can certainly see that it's sort of a torus that's almost edge-on here. And this is a huge, huge disk. It's 370 AU across, which is 5 times the size of our solar system. So this is still very much a huge disk. So now, as the late great Tom Magliozzi said, reality often astonishes theory. I have given you a nice story and even some data to back it up, but because we have to do more than just talk about the high levels of how star formation works, let's talk about the things that don't work, the things that we don't understand. This is one of them. So the story that I've told you starts with a big disk that thins out steadily and eventually forms planets, which seems to make a lot of sense. Here we have, though, things that complicate matters. I have disk brightness here as a function of age here. And so at a certain point, when the star gets old enough, there's no disk left. So the story that I've told you is this overall steady decrease of disk mass, in other words, disk brightness, as a function of time. But look at how many young stars don't have disks. Why? Why do some stars shed their disks so early, and some stars hold on to them for so much longer? We do not know. All the stars that are here are A stars, and things might be a little bit different if you go to F stars, G stars, K stars, M stars, but still, there's a significant number of stars that have shed their disks at very young ages. Nobody knows why. So there really is a broad range of disk lifetimes. And somehow the rocky objects smash into each other and merge into larger bodies. Again, nobody understands exactly how that works. In the lab and in calculations, it's pretty easy to get up to millimeter, centimeter size rocks. It's really hard to get larger rocks. It's because what happens is there's usually so much energy that the things smash into each other and break apart rather than merge. So no one really understands how that works. But certainly the collisions are going to cause clouds of dust, and you're going to end up with these debris disks, so-called debris disks, where you have debris from these collisions spread out into the disk. And certainly what's going on is that you have the dust that's warmed by the central star, which is what's glowing in the infrared. But the fact that there's huge amounts of debris in these disks up to the age of even 100 to 200 million years, it's just really confusing because theory is predicting about 10 million years. So why do they still have big disks 10 times later than that? It's really confusing. And the fact that even some of the youngest stars have no debris, it's really confusing. And so there's a very large range of properties from star to star. Why? Why are some stars different than others? It's really not clear. And some people have begun to suggest that maybe you have just single, humongous collisions that produce all the debris that we see in some of these older systems. So systems more like our sun, a lot of stars like our sun, have dusty disks. More than half of them have dusty disks. And does that immediately mean that lots of them have rocky planets? We don't know. There's certainly lots and lots of water found in these clouds around young stars. Is that the water that gets caught up into planets, or does that water boil off and not get caught up into planets? Our moon formed from a giant collision between two planetesimals in our young solar system. But a lot of stars that are now at that age don't seem to have a lot of that dust. And that could mean that there are not a lot of rocky planets with large moons in the universe. That is really important because a lot of people think that in order for life to have evolved, once you get life in the oceans, in order to get life on the land, Tides are absolutely critical because those critters that live at the tidal boundaries have to be able to cope with sometimes being wet and sometimes being dry. And that seems to have been critical for life to have evolved. And so that may mean that having large moons is critical for a rocky planet to have life. But the fact that a lot of the stars that are now at the same age as we were when we got our moon don't seem to have lots of dust. So what does that mean for the frequency of moons and tides on rocky planets in the rest of the universe? Here's more spectroscopy looking at the outer disks of young stars. So here again, I've got brightness as a function of wavelength. This here is a spectrum of the disk around HD 69830. And all of that brighter green, all of those brighter green emission, the things that colored brighter green, are emission lines from something that astronomers call forsterite, which you might know as olivine. There's its chemical composition. You can see the bumps and wiggles in the spectrum are matched really well by the bumps and wiggles in the spectrum of comet Hale-Bopp. So the stuff that goes into making the comet Hale-Bopp is also the stuff that's going into the outer disk of this star. You might naturally ask, well, is this a single comet? Well, the people in this paper go through the math, and they show this can't be a single comet. It has to be a substantial outer disk. But still, it's really fascinating. The outer disks look just like comets that are in our solar system. In fact, it could be really important to have these comets to bring water to Earth. So it had been thought that comets could not have brought more than about 10% of Earth's water, and with asteroids bringing most of the water, which is really peculiar because you think of comets as being icier than asteroids, and yet somehow asteroids are bringing us most of the water. That's based on observations of the ratio of deuterium to hydrogen and trying to understand, because deuterium is really easy to break apart. So the deuterium to hydrogen ratio is really critical for understanding where where the water source is coming from. So Herschel had observed a Kuiper Belt object and found that it has about an Earth-type ratio of deuterium to hydrogen, which suggests there's a large reservoir of Earth-like water in our outer solar system. The problem is that the jury is very much still out. Here is the deuterium to hydrogen ratio. There's the Earth's deuterium to hydrogen ratio, and this is our best understanding of what the protosolar nebula deuterium to hydrogen ratio must have been. So clearly the Earth is getting its water from a different source than the rest of the nebula. Jupiter and Saturn are much like the protosolar nebula. Uranus and Neptune are not not close to the, it's a little bit different than the ratio found for Jupiter and Saturn, but they're not Earth-like either. Asteroids, however, are very Earth-like, and so that had been the evidence that Earth was getting much of its water from asteroids. Enceladus is a moon. And here we have a whole bunch of these long period comets which have too much deuterium to suggest that they were the source of Earth's water. This is the data point from Herschel, which said, oh yeah, no, these long period comets could have brought Earth's water because it does have the right deuterium to hydrogen ratio. You may have heard of Rosetta, which actually landed a little probe called Philae on the surface of a comet. And Rosetta says, no, this is the deuterium to hydrogen ratio that it found for comet 67P. And so they say, no, asteroids still have to be the dominant source, not Jupiter family comets. So clearly the jury is still out as to exactly where we got all of our water. And maybe in the end we still need comets because there are some very recent results that are looking at the physics of the impact and saying that the prebiotic chemistry could have been produced by the impact itself. What they're saying is that comets have a variety of simple molecules such as water, ammonia, methanol, and carbon dioxide, and an impact could give that enough energy to drive all sorts of interesting chemical reactions. You do have to be careful though, because comets hitting straight on would actually just blow things apart. But some of them have glancing blows, which would give it just the right amount of energy to drive these interesting chemical reactions. So you may be familiar with Luke Skywalker on his planet of Tatooine, and he goes out to look at a double sunset. How common is this? Turns out might be pretty common. If the stars are close enough, you can get a disk around both stars from which you could form planets. Sort of middling distances, the interactions between these two stars disrupt the disks until you don't get a disk. Even further still, you end up with a disk around one, but not the other. So it is possible that you have planets around binaries. And in fact, Kepler is finding circumbinary planets. So maybe there really is a Tatooine out there. They haven't found a rocky circumbinary planet yet, but I'm sure it's only a matter of time before you end up with a circumbinary rocky planet. Continuing in science fiction vein, Epsilon Eridani is supposed to be Vulcan, Spock's homeworld, and it turns out to have a pretty similar system to us. Epsilon Eridani is our closest known planetary system, only 10 light years away, which in the Star Trek universe accounts for the Vulcans and the humans getting along so well, because we're next door neighbors. Here we have the inner solar system, where we have the star in the center, our sun, rocky planets, an asteroid belt, and then a gas giant to shepherd it. The inner Epsilon Eridani system, we don't know if there's inner rocky planets, but there is definitely an inner asteroid belt and a gas giant that shepherds the asteroid belt. Going out further, we have several gas giants and a Kuiper Belt in our solar system. In the Epsilon Eridani system, there's a big gap in between this inner dust ring and the outer dust ring, and so it's proposed that there are planets in there, just like our gas giants, creating that gap. So who knows? Maybe there is a Vulcan out there anyway. So is there dust in our solar system? You betcha. Plenty of dust. This is another view of our galaxy, similar to what I showed you a couple movies back. Here we have the galactic plane here, and this is that same projection where the galactic plane is flat, and this S-shaped blue thing is the hot dust in our solar system. In this case, this isn't IRAS data, this is COBE data, but still, you're looking at the dust from our solar system. And in fact, astronomers love making up their own units. Our dust in our solar system is called the zodiacal light, and you can see it if you get out to a very, very dark place. You might see it as the beginnings of sunrise, but it's not. It is our zodiacal light. It is the dust in our solar system scattering sunlight to us, but you have to be very dark, like a moonless night in the desert, in order to see it. This right here is the zodiacal light, and this is our galaxy. Astronomers love defining units, and so the amount of dust that we think we have in our solar system has been declared to be 1 zodi. And so when you talk about the amount of dust in other solar systems, you might say, oh, well, it has 2 zodis worth of dust. So as the last few slides, I have a couple of movies that are models of star formation. I am not a theorist, I'm an observer. I don't do models of star formation, and I don't understand the details, but Matthew Bate is a really good theorist that has all sorts of movies that look exactly like you think star formation should form. So there's the beginnings of star formation. You have the matter falling in, you've got condensations. Here you have, this is density on this side and this is temperature on this side. So you have condensations forming, you have these ribbons that are of star formation, and then the stuff is of course moving, and so the stuff is interacting with each other and disrupting disks and throwing out, in fact ejecting stars entirely from the system. So you end up with really, really complex systems, and these systems are interacting and disrupting the disks, and of course changing the chemistry and changing the planetary dynamics of the stuff that's forming in those disks. So this last movie is just looking at, an entire cloud as things are starting to collapse, and you end up with filaments that result in lines, rows of stars. And this is what I'm pretty sure is happening in IC 417. You end up with that filament, that long stringy filament that goes off to the left in our pictures, that is almost certainly one of these kinds of filaments. And remember, we have in some of these papers discussion about how there are clusters pushing around the gas and dust in IC 417. So we've got a cluster that's on the right of our image, that's pushing the gas and dust to the left. Then you have something that's above our region pushing the gas and dust down, creating the filament that goes off to the left. But it's the same sort of thing as you see in these movies here.